Hello everyone. My name is Lu. I'm a PhD student at Technical University of Munich. And today I'm gonna talk about our 3DV paper. Unfortunately, I wasn't able to attend the conference in person, and I'm really appreciate that Voxel 51 invite me for this talk, and that I can share our work a little bit. So the topic is about physical realistic 4D generation. So before I dive into the work, I want to talk about our motivation first a little bit. Let's look at the generation dimensional landscape. So for 1D, we have a very mature large language model to generate the text. And for 2D, we also have like a lot of product ready stuff like Nano Banana from Google. It's also quite mature. And for 3D, it's now happening. Like we have some company have very nice large model like from like Hunyuan 3D from Tencent. They can generate nice 3D assets from a single image. So we are thinking about what happened next. So we think, especially nowadays, people talk about word model a lot, and we do think that if we want to represent the word, we have to be able to deal with motions and dynamic shapes. That's why our focus is on 4D dynamic shapes. So we do think the 4D generation has fewer realistic applications, but it's essential for the future applications. And we also want our 4D generation to be physically plausible, controllable, and geometry consistent. Why we really focusing on physically plausible? The reason is if we look at this image, so someone can already quite uh, fast sense that it's not a photo, it's a generated image. Why? There are some physical detail wrong. For example, the shadow is wrong and the vanishing point is wrong. Like the perspective of the image is actually not correct. So we think that the 3D world naturally embeds emotions and physical laws. And human perception is very sensible to this. So that's why we think if we want to generate some 4D emotions, it should be physically plausible, controllable, and have geometry consistent and texture consistent. So we have some work to tackle this problem before our 3D work. So we have two papers to tackle the 3D to 4D task. So the task is basically if we have some sparse temporal sequence of the point cloud as input, and can we generate realistic intermediate shapes and motions? And can we generalize this interpolated result to the real world data? The answer is yes. For example, like for this example, we take some key frame point cloud as input, and we can already, like the first column, and we can already generate very smooth motion and we can recover the mesh in the third column, and we can directly infer on the real world data. Like the real world data is input real world data is the second column, and we can directly get the very smooth motions in the real world data. So how do we do that? To solve this problem, we need to think about two things. First is how to represent geometry. Second thing is how to represent the motion. So we actually choose to represent the geometry using implicit representation. Basically, it's Sandisk function. But to be able to represent the dynamic shapes, we not only need the input of the 3D location, we also need the input of the time step. So we use time variant implicit representation to represent the geometry. And we use a velocity to represent the motion. The reason is that basically you can see as shown in this image, if we have one point, and the point move over time, and it's always stay on the surface of the shape. So for your implicit function, it's gonna always give you zero as a output because it's on the surfaces along the time. So any time point and time step is give you zero. But if we take the time derivative of this implicit function, we naturally actually get a velocity field out of it. Like the partial derivative of your implicit function and plus the velocity times the derivative of your implicit function is actually zero. So if you so we naturally have the implicit velocity field here coupled with the implicit net. And if you know something about the smoothness function, you know that actually the gradient of the smoothness function on the surfaces is a normal direction. So it's a very nice geometry constraint there. And by the way, if you have questions, you can just interrupt me. I can also answer. And so that's basically our motivation to use the implicit method and velocity to represent the geometry and the motion. So we designed the pipeline like this. So the key point is that we actually use implicit net to represent the geometry and using the velocity net to represent the motion. And we have the implicit net to offer some geometrical constraints, and using the velocity net to offer some physical constraints to make sure the movement is physically plausible. And the output is SDF, which allows us to extract mesh out of it, and we can have the deformed mesh. And the velocity field, which allows us to move the point cloud. And the latent space, it just allows us to deal with sequence of input. A little bit dive into the physical constraints. So we basically, so for the physical constraints, we mean that we have some constraints like volume preserving, like divergence free. And we also have some spatial smoothness over our velocity field, which basically saying that 2 points, if they are close in space, the velocity shouldn't change too much. And we also have distortion constraints, which basically helps us to get rid of the weird twist when we estimate the motions. And we also have this stretching constraints. Is this as shown in this figure? It's basically saying that we want the motion will happen on the normal direction instead of tangent direction, because the tangent direction is more shearing, but we want more motion, like more movement. So that's the idea of this physical constraints. So using this and the very nice coupling of velocity field and implicit field, we get some nice results. So basically, if we just have a source point cloud and a target point cloud, we can already nicely recover the movement. And nice thing about the method is that we are not constrained by its either rigid deformation or non-rigid deformation. We can deal with both without this like switch method or add something else. And we can also deal with large deformation, which other papers struggled with. We can also deal with partial shapes. Is there some question or okay? With deal with partial shapes. So even the target point cloud is not complete observed, we can still recover the motion. And we can also extend our method to the sequence input and also the real world data. So basically, for example, this data set, they basically film a human movement using a lot of RGBD image, and they fuse them to get the Kinect point cloud, which is very noisy. And they also offer a approximate registration. So we train on this approximated registration, and we can directly get the smooth movements and recover the mesh, and we can directly infer on the real world data to move the real world data. So basically, I think it's very hard to directly deal with super noisy Kinect data, but using our method is actually quite easy. We can also deal with the high resolution meshes. For this, like the first column and third column is the input. It's also a approximate registration. And we train on this approximate registration. It's only for every point cloud, it's only like 5,000 points. And we train on it, but we can directly infer on the very high resolution output mesh. I think every mesh has like 20,000 vertices, but we don't really need to directly train on the real world mesh, but we can directly infer it. And it's very fast because the structure of implicit net and velocity net is quite simple. It's just MLP. So every pair, the training of every pair takes less than 2 minutes, and the inference time is almost real time. So it's very efficient. Mm, and after we have done this task, like from 3D to 4D, we start to think, can we go one step further? How about like 2D to 4D generation? Because if you imagine the input data, it's still a lot of requirement that you have a 3D data like point cloud or like low resolution mesh. But for image, it's a very cheap input. Like everyone have a phone and you can just take a photo and if it would be super nice that if we can directly generate 2D to 4D. So the answer is actually yes. If we have a pair of image, we can actually directly recover 3D model and 4D motion from just a pair of images. So here is the example. It's actually the image of my cat. I took it, I think it's in separate day. It's not even like continuously I took it. It's actually I took the image in separate day, but we can also yeah, that's the problem. Yes, we can recover the motion, but unfortunately, my cat he does have tail, for example, for the record, but somehow uh, the 3D generation is not that successful, I guess. So basically, the that's our work on the 3DV. It's a 4D generation from 2D image pairs. And the method works like this. So we have a pair of image and we have a 3D generation model to recover the mesh. And from the mesh, we actually uh, extract the feature of the vertices, and we have a correspondence estimation module to estimate the correspondence. But we only need the sparse correspondence. We don't really need a dense correspondence. After we estimate the sparse correspondence, we can actually train on the point cloud. We actually don't really train on meshes. And instead of using both implicit net and velocity net, for this task, we choose to only keep the velocity net and the physical constraints. The reason is that we already generate a mesh. So we think we don't actually need the extra burden to estimate a mesh, like using the velocity, using the implicit net to estimate the SDF again. So we can directly deform the mesh actually using our velocity net. So using this pipeline, and we can directly for the output, we can actually directly inference on the high resolution textured meshes, and we can like kind of like the byproduct is the point tracking. Yeah. So for this, we can actually recover the motion of any object. Actually, we don't really need any template. So for example, like the spoon and the golf, like the movement, and it's not really need to be only one object. Actually, like it can be someone hold something. But for the record, we never tried if it's two separate objects they are not attached to each other. We haven't tried this part. It would be nice to try, but I will put it in the future work, I guess. Yeah, and that's basically the result of the method. And also a little bit insight that why we are not using image morphing. So basically a natural thought to solve 2D to 2D to 4D is that people will think, okay, we can either take a video as input, like we have a video, it's a motion is there, and we use video and generate each 3D from each frame of the video, then we can get the 4D. It's basically the same idea that we use image morphing first and we generate the 4D video. So image morphing is that you basically deform the image from one to a second one to create a continuous deformation of the image. The reason is that first, if like for example like this image, this pair of image, they are actually in different texture. So if we directly use image morphing, we deform the first image to the second one, the texture is also deformed. It's basically kind of like from one horse to another one. But we think it's a very nice feature of our work is that we can actually use the second image as a motion template. which means that we always keep the texture of the first image and we only adopt the motion of the second image, which allows us, like the first line is the image morphing, and we generate the 3D 3D mesh from the deformed image. So the generated 3D mesh will adopt the texture of the each image. But for our method, because we always deform from the first generated mesh to the second one, but we only keep the texture from the first image. So we have actually very nice, like naturally texture consistent. And also that's why basically for our method, it's we think it's a very nice feature that we can actually you can just basically take a pair of arbitrary image and we say, okay, we want the horse, the the horse starting point is like the image one, and we basically want the image like the want the motion to be like the image two, but it's haven't don't need to be same horses actually. And also compared to the video generation method, our result is actually more, I would say, more smooth. It's a very nice video to 4D generation method. It's V2M4. And for them, they take a video as input and they generate the motion and the textured mesh. For our method, we actually don't need a whole video, so we only need the keyframe. For example, their input is basically 30 frames, I think. We only need 1/5 of it. We only use five keyframes to generate the smooth motions. And I think the video generation, like the video to 4D generation, the key idea is relative similar to the image morphing. Like you basically generate 3D mesh for each frame of the video, and you have some extra constraints to force the texture and the geometry is consistent. But for our method, we naturally can have the texture consistent and also geometry consistent method. Another very good thing for our method is that the output FPS, like the frame rate, is actually very you don't need to retrain it because it's a time step, so you can define it in your inference time. Like you want the FPS is 30 or you want FPS is 10, you just set the time step as 30 time step or time step is 10 or something like that. You don't need to retrain it. But if you use the image morphing or like video method, maybe you need to retrain it because you need to first generate different FPS, deform the image, and then generate your 3D again. So for us, for our method, I think it's a very big advantage. And you can also observe our motion is more smooth. We don't have some flicking, and our geometry is very consistent. And here is another example. Like for example, like if you observe the bird, I think for us our geometry actually is stay consistent. And for the video to 4D generation, I think the geometry is a little bit weird here. That's basically the result of our method. And what we also think about what can be done to further improve our method. To share a little bit thought is that first let's summarize the key contributions. So we think to best of our knowledge, we probably the first approach that generate a complete 4D sequence from just an arbitrary pair of images. And our generated motion is physically plausible. And we only need a very simple input data. Like we just need a pair of image. We don't no depth, no video. And we are not template based, which means we can deal with arbitrary object, not constrained on only human or just one species or animals or something like that. And to think about further improvement, we think there's something we could also consider is that first, our method is only for the object. It's a very big constraint, I would say. It would be nice to be able to deal with dynamic things. That would be much cooler. And also now our method is still physical rule based that we make a lot of physical constraints assumption, like for example, volume preserving or something like that. It's actually a big constraint. And it would be much nicer if we have some learned physical constraints that allows us to deal more complicated motions. Now I think our method only works on relative simple motions. We haven't really tried like super crazy deformation. And we also want to combine the motion generation method to our method because our method is uh, like the result, the because of the physical constraints, the result always give you like the shortest possible motion. Like, of course, it's physically plausible, but it's short, almost the shortest movement you can have during this two pair of image. We want to actually have a plugin system that allows to have like more controllable, which like our method to give you only like those very physically plausible constraint motions. We also want to allow user or like our method to generate more diversity of the motions, like maybe like human motion generation method that they can actually generate from the past. They can generate different future or something like that. Would be also very cool to have. And for the long-term vision, we would say it would be nice to have a complete pipeline that we can casually using 1D or 2D as a input, like a photo or sketch or short clip. Then we can directly output a product ready for the asset and texture and physical constants. We think it would have very nice applications. That's all from my presentation. So if you have any questions, you can
Thank
ask
you
me.
so much,
Thank you.
Lou. Yeah, there are a few questions in the chat. I'm gonna try to group some of them together. Some questions are quite similar. There's a question here about constraints, specifically on the modeled forces and on motion recovery. So, for example, if a small ball hits something, could it cause a larger ball to move? So, I guess the constraints regarding motion recovery and modeled forces. How does
Can you, sorry, I didn't really get the question. Can you say that again? Like
Yeah, so
if
there's two questions about the
Mhm.
constraints of the model. One is
Mhm.
constraints on modeled forces. For example, if a small ball hits something, could it cause a larger ball to move more? And
Mm,
I guess kind of in line with that is this question about motion recovery. It just says, how do constraints affect motion recovery?
mm. It's actually good questions. Because it's we for our method now we're only dealing with object movements, so we haven't really touched like the if the two objects interact with each other. So if like a ball, if one ball hit another one or something like this, we actually haven't really get touched that part yet. So if the movement of the single object, we can dealing with it. So basically, yeah.
Cool. So there's a question here. More so about lighting, I guess. So, what about lighting? For example, if a horse walks under a tree, the initial texture would be incorrect. And then also there's another question about how shadows are handled when we're going from 2D to 4D.
Mm. So I guess for the shadow part, it's not a view synthesis method. So actually, we never need to deal with shadows because it's a single object, right? And then unless it's a self shadow, like the object casts shadow to itself, then maybe on the texture part, we need to deal with it. Otherwise, if the shadow cast to the ground or to the background, then we actually don't need to touch that part because the output is a 3D move 3D mesh, and you can basically have the 3D mesh at each time steps. So yeah, unless the shadow is casted to the like to itself, as it's become part of the texture. Otherwise, we don't really need to deal with it. But it's actually a very good question because I don't think we actually model that part. So it would be a constraint to our method. Like if it's casted shadow to itself, when the when it's moved, if the shadow is actually need to move, it's probably gonna cause some problem. Because our method basically treat the shadow as a part of the texture. Yeah.
Awesome. And a question here, you might have touched on it during the talk, but it's what was the loss function that was used? And then how was the loss function modeled in this method?
Actually, the loss function, I basically delete all the equations because I thought nobody really uh, liked the equations. But actually, I think the loss function is basically those. I don't have the equation here, but basically those, like those 1, 2, 5, 3, 4, 7 losses. So the equation, level set equation constants is this one, like. Where it is. Is this one like the partial derivative or your Sandis function velocity field times the gradient of your implicit is 0. One is this one, like you add the L1 loss to this part, and uh, and also like those one, like volume preserving is the divergence of your velocity is equal to 0. So something like this. Yeah.